Okay, thank you. Yes, thank you very much to the organizers for giving me a chance to speak and putting up with the fact that I have to do it online. So unfortunately, there's some administrative hiccup that prevented me from coming in person. I know that the title here is not modest, so I kind of apologize for that, but I wanted to pique everybody's interest. And it is true that we will see that in this story, kind of very different ideas and concepts show up all at once. I hope to be able to convey that to you. This work is done in collaboration with Sirui Shuai, who is my graduate student, Yixu Wang, who is my postdoc, and Daiming Zhang, who is a truly amazing undergraduate that is applying currently for graduate schools. So you would be lucky if he chose to work to join your graduate program. Please remember that name. And here are those collaborators and their pictures. So without further ado, let's start the main part of the talk. So this talk is about the minimal cut prescription for computing the entanglement entropies of subsystems. This minimal cut prescription is familiar to us from the Ryuta-Kayanagi proposal, which is the most well-known example of it. So if you have a system which is in some quantum state, and that quantum state is represented by some higher dimensional bulk structure, typically we mean a gravitational spacetime in holographic duality. But more abstractly or more generally, we could just think about some tensor networks. For example, random tensor networks have a property that I want. Then entanglement entropies of boundary subsystems can often be computed by finding a minimal cut through that bulk structure which prepares the state. So a minimal cut through a time slice of a holographic geometry is what gives us boundary entanglement entropies under the Ryuta-Kayanagi proposal. If you have a random tensor network at large bond dimension, you have a similar statement where finding the minimal cut through that tensor network gives you an exponentially good estimate, in the sense that corrections will be exponentially small to the entanglement entropy of any given subsystem. And so it's this class of states, not all states in quantum mechanics, but this class of states which are the states of interest for me in my talk. And if there are any questions, then please interrupt me. Here I'm just trying to establish what the context is for the talk. Just to be clear, because as part of my flamboyant title, I mentioned erasure correction. Not yet. Sorry about that. It turns out that just because I have this minimal cut prescription for entanglement entropies, I can, just from that simple fact, I can derive certain relations between those entanglement entropies. And so in this slide, I proposed I review the simplest example of that fact that we can go from the minimal cut prescription directly to writing down certain constraints on the boundary subsystems. So let's apply the minimal cut prescription to some system A and to another system B. So it gives us that red minimal surface and the green minimal surface for the A and B. And now let's ask what might be the entanglement entropy for the combined system AB. Using the minimal cut prescription, I would have two candidates, of which I have to find to pick the minimal one. So what are the what are the two candidates? One of them is just reusing the surfaces for the A and B separately. This is one locally minimal, not necessarily globally minimal, but locally minimal surface for A and B. So that's what I write here, SA plus SB. But there's another candidate solution which sort of connects A and B together, and that's the one that I have drawn here in purple. So that's the other candidate. And the minimal cut prescription tells me that the entanglement entropy of the combined system AB is the smaller of these two quantities. plus SB or something smaller than it. One way or the other, SAB is less than or equal to SA plus SB. This relationship is known as subadditivity of entanglement entropy, and we have just proved it as basically a one-liner and a single picture. This is not a general proof of subadditivity, because subadditivity as a statement holds in all of quantum mechanics. Not all states in quantum mechanics obey the minimal cut prescription. Here we have proved it for the subset of states which do obey the minimal cut prescription, and as we know from our studies on holography, for example, these would be states that are dual to semi-classical geometries, or random tensor network states, or perhaps some other states where some other bulk structure would be relevant. Long story short, if you go back to the proof of subadditivity, which has been known since 1971, you see that it's kind of complex. Here we just have a simple one-liner, and so there's a statement that, or we get a feeling that states that do obey the minimal cut prescription, such as holographic states, make some certain statements easier to prove, or maybe they manifest them more explicitly, or more manifestly realize certain facts that would be true about quantum mechanics. This is the idea that we can gather from this simple example. In fact, that way of thinking is perhaps not ideally correct, because, as it turns out, you can derive in a similar fashion a larger host of inequalities, but this larger host of inequalities will not be generally true for all states in quantum mechanics. So it's not just, or not necessarily, that the minimal cut prescription manifests certain general properties of quantum mechanics more manifestly. It may be that it often comes with its own set of constraints. And it's this own set of constraints that I would like to study in this talk. How do we understand those constraints? I propose to think of them as necessary conditions for minimal cut to work, since we derive them from the minimal cut prescription, and they are necessary conditions for it. And so if you violate the inequalities in question, then your state necessarily is not of the minimal cut type. I use the word minimal cut here, but I remind you that my primary motivation is holographic, so mostly I mean here states which are dual to semi-classical geometries in the ADS-CFT correspondence. So in that sense, I will be talking here about necessary conditions for states in the holographic CFT to have a semi-classical dual. Next, word about the interpretation of these inequalities. So someplace in the title, I mentioned erasure correction, and in this slide, I just wanted to briefly explain why I reference erasure correction as part of this story. So let's consider this setup where I divided the boundary of let's say, of an equal time size of a holographic CFT2, just for specificity, into 4 parts, A, B, C, and D, and I compute their entanglement entropies by a minimal cut prescription, and I have these 2 options. Either I'm in this option where A and B are in the disconnected phase like this, or I'm in the other option where C and D are in the disconnected phase. So that's an application of what we saw on one of the previous slides. In each of those cases, it is true that the degrees of freedom, the bulk degrees of freedom that sit in the middle of this holographic geometry are protected against some erasure. In the left case, they are protected against the erasure of A and B, because these degrees of freedom live in the entanglement wedge of C and D. In the other case, they are protected against the erasure of C and D, because they live in the entanglement wedge of A and B. So you can forget about C and D and still recover them. Depending on which Ryuta-Kayanagi surface you have, you will have different types of erasure correction, but you will also have different types of inequalities being saturated. In this case, we saturate subadditivity on A and B. In this case, we saturate subadditivity on C and D. So I would like you to keep in mind that whenever I tell you about these inequalities, which are necessary conditions for a semi-classical bulk geometry, you should remember that every statement I make has some interpretation in terms of a phase transition, such as this one, between this configuration and that one, and those phase transitions will always tell me about
some region in the bulk being corrected or not corrected against the erasure of something. So all of these inequalities deep down have an interpretation in terms of error correcting properties of that holographic code. So with these preliminary remarks under our belt, let me actually go to the real inequalities. So here is the state of the game as of a few months ago. We had from Sergio Hernandez Cuenca, this should be an H and not an F, we have 8 known holographic entropy inequalities, which can be derived by the same kind of logic as we have seen on this slide. Basically, a more sophisticated version of this argument, a much more sophisticated version of this argument, gives rise to this set of inequalities on more than, now in this case, on 5 regions A, B, C, D, E. My work with another undergraduate student who is also applying to graduate schools this way, Yixu Wang, revealed that there is, we found this new inequality, which I wrote here for you in full detail. That was a year ago. And then in September, Sergio Hernandez Cuenca and Veronica Hubini and Frederick Jia announced 373 other inequalities. Obviously, that's a list which is too long for me to write down for you here. So there's some long list that they have made. And so these are the inequalities that people have known prior to this work, which I am presenting today. So here I want to make some comments, which is that when I look at this table, I am both impressed and disappointed. I hope that you will share my feelings and my reaction to it. I'm impressed because it is an impressive feat that humans have been able to come up with these relations, which are very non-trivial to find. And some of them, I mean, especially this inequality number 6, just appears formidably complicated with coefficients and whatnot. So kind of impressive. But then, see, I'm talking about work by other people, so I can use the word impressive without worrying about being modest or immodest. So I think it's very impressive. But on the other hand, I'm also kind of disappointed because it seems very difficult to hope for or very unlikely to hope for an interpretation of these inequalities. So when I talk to people about the program of discovering these inequalities, I often encounter the question, okay, suppose that you wrote them all down. What would you do then? So this is a sample of that question. We look at this table and we say, okay, we have these inequalities. What can we do with them? And so my goal in this talk is to bring some order into this table and try to reveal a certain structure which underlies this table. And I hope that I will convince you that this table actually comes from some very interesting, both mathematics and physics, which is well organized, studied, and reveals some unknown facts about, well, really about holographic error correcting codes. So that's my goal for today. I think this is a time when I can, when it would be good to ask for questions. Okay, if there are no questions, then I'll just keep going. I don't see the audience. It's hard for me to gauge where the audience is, but I hope that you're still there, and I hope that some people are paying attention. If there are any questions, then please raise them. Okay, so I'll just proceed. So I said that this is the state of affairs as of a few months ago. So my students and I and Yixu, my postdoc, we just felt that there weren't enough inequalities, so we should discover some more. And so here are the new inequalities that we proposed. And just so that you have you're oriented about where we're going, I will tell you about these inequalities, and I'll try to give you a question, an answer to the question why they are there and what they mean. But first, what are the inequalities? So we found these new inequalities, which take the following form. Here is one family of them. These are 2 infinite families of inequalities. The first family is parametrized by 2 odd integers, m and n. The second one is parametrized by 1 single integer, but it's an arbitrary integer, odd or even. I call them the toric inequalities and the projective inequalities. To understand what the projective plane inequalities, to understand the structure of these or what these inequalities mean, we do need just a little bit of notation. So I ask you to be patient for just 1 minute while I explain the notation. I promise that after this, there won't be any notational quagmires. So, we have two types of regions, which are called AI and BJ, which are indexed with some indices like A1, A2, A3, and so on. AIK is a set of k consecutively ordered regions starting from AI. So there you go, this. And then BJL is the same type of thing on the B-type regions. Again, we have A-type regions and we have B-type regions. The total number of A-type regions is M. The total number of B-type regions is N. So that's why we have these two numbers there. And in addition, I have one final piece of notation, which is that if M and N are odd, then it makes sense to talk about the smallest consecutive majority of A-type regions and the largest consecutive minority of A-type regions. And that's what the notation A plus minus I means. So the smallest consecutive majority of regions would be M plus 1 over 2 of them, and hence this. And largest consecutive minority would be M minus 1 over 2 of them, and that explains the notation. So with this understanding that AIK and AI plus minus, same thing for the B's, correspond to or denote families of however many consecutive regions A, we are now in the position to understand what these inequalities mean. So there is an inequality like this, and there is a family of inequalities like that. Now I call them the toric inequalities and the projective plane inequalities. So why those words? Why the torus and why the projective plane? Before doing this, let me just give you a feeling for what the toric inequality for m equals 5 and n equals 3 looks like. There are 5 times 3 terms of one type, greater than equal than 5 plus 3 terms on the 5 times 3 terms on the other side, plus 1 additional special term. So the fact that this thing is arranged, this is a special case of this inequality when m and n are equal to 5 and 3. So if you stare at this, you see that there is some kind of rotational symmetry that acts on the A's and acts on the B's. You have A1, A2, A3, A3, A4, A5, A5, A1, A2. There's a pattern here which kind of rotationally repeats itself over the A's and over the B's, over the A's horizontally and over the B's vertically. So you can see that there might be some reason why I would call this a toric inequality, simply because these terms are arranged into these types of arrays, which obviously have periodic aspects to them. Well, let's be a little more precise about this. So in being more precise, I'm going to take the inequality and draw every term of the inequality that sits on the greater than side of it as a face of a graph, and every term that lives on the right-hand side, the less than side of the inequality, as a vertex of some graph embedded on what? Embedded on a torus. And so I have done it here for you, again, in the special case where I have 5 A's and 3 B's. And you see that there's a pattern of repeating regions which have however many A's and B's on the faces and 1 less A's and the same number of B's on the vertices. And this pattern repeats itself, obviously, periodically. When I can now ask, what is the fundamental domain which covers each term in this inequality precisely once? And I have highlighted such a fundamental domain for you here. This is a torus, which comes from a periodic identification applied to an infinite plane. And so this is the reason why I would call these inequalities toric inequalities, because they admit this type of representation in terms of a graph. Are there any questions about what I'm saying? So let's apply, if there are no questions, then let me apply the same thing to the next family, to the other family of inequalities. So for the toric ones, it may have been kind of easy to see why they are toric, but for these ones, I bet you that it's not so easy to see why I would want to call them projective plane inequalities. But here is a picture that reveals why. So I have taken all the terms in these inequalities. Again, there is the rule that I'm using is that left-hand side, so greater than side terms are the faces, and the less than side terms are the nodes or the vertices of a graph. And I have laid out all of these terms in the form of a graph, or really my student Sirui did it. And this is the pattern that we see. This pattern repeats itself. And when I look at how it repeats itself, I see that basically it forms a strip where there is a certain boundary of a strip. But there is more to it. On the strip, there is a repetition of terms. So I have highlighted identical terms with the same color here. And you see that the same colors appear here and here in the same way, but in the opposite order. And so if I were to ask what is a single fundamental domain of this for this inequality based on this graph, then I would say that it comes from a strip which is further, which is modded out by a finite translation along the strip, such as this, and an additional flip or an additional inversion, an additional twist. So that means that our inequality is basically lives on a Mobius strip. We took a strip and an infinite strip, and we have modded it out by a translation times a flip, an orientation change. So we now have a Mobius strip, but that's not the end of it, because now I look at the boundary of this Mobius strip. So this boundary is basically this set of terms and these set of terms. It looks like two boundaries, but after the modding out by the Z2 flip, this is basically a single S1, which is the boundary of a Mobius strip. And now I realize that on this boundary of the Mobius strip, all of these terms are exactly the same. You might say, oh, I see A1, A2, A3, A4. Here I see B1, B2, B3, B4. Well, I'm working in a context where the A's and B's together are in a pure state. So these are complementary terms, and therefore they represent exactly the same entropy. So these faces are secretly one and the same face. If I have a Mobius strip whose boundary is basically a single face, then that's equivalent to saying that I have glued my Mobius strip to a disk, and that makes up a projective plane. And so this is an explanation for why these inequalities secretly encode or are governed by the topology of the projective plane. They define graphs which are embedded on the projective plane. Are there any questions about what I just said? So I will ask myself a question, since no one is, one more thing. So if we go back to the table of inequalities, which I said is both impressive and kind of disappointing, then you will see that there is other inequality there, which is this one over here. You can play the same game and say, if I put it up on a graph like I did before, what kind of structure will I get? And it turns out to fill in this part of a tessellation of the hyperbolic disk. And this is, again, a subgraph of the tessellation of the hyperbolic disk, which periodically repeats itself. In other words, the graph itself, which represents this, this inequality, would have the topology of the hyperbolic disk modded out by a certain symmetry. After you go through the computation and see what you get after you take a single fundamental domain, which just covers each of the terms in the inequality once, then you don't get an infinite hyperbolic disk. You get some finite surface, which is some compact surface, which is a quotient of the hyperbolic disk by a certain symmetry. What is that surface? It turns out that that surface is the genus equals 2 Riemann surface. So this inequality lives on the G equals 2 Riemann surface. Specifically because the inequality defines for me a set of faces and vertices and a graph that has that realization, then it also defines a polytope with the topology of a G equals 2 Riemann surface. And what is that polytope? Well, if you look it up on Wikipedia, turns out that it has a name, and that name is Cubohemioctahedron. And so I put the title, the word Cubohemioctahedron in the title, kind of for the fun of it, but this is the place where it makes an appearance, is this analysis. Apparently, the topology of this inequality is the topology of a cubohemioctahedron, which is a polytope embedded or realizing the G equals 2 topology, a polytope of genus 2. Are there any questions about what I just said? So to summarize, so far we have looked at some new inequalities that my collaborators and I discovered. We also looked at some old inequalities that were known from before, and we have found that they are related to graphs on Riemann surfaces, or maybe not Riemann surfaces, there's also the projective plane. They are graphs on two-dimensional surfaces, and those graphs on two-dimensional surfaces have the property that, or the way that they encode the inequalities is that vertices correspond to right-hand side terms, so the less than side terms in the inequality, whereas the faces correspond to the left-hand side, the greater than side terms of the inequality.
Hey, Bartek.
This is not enough to tell you how to construct that graph. So in the next slide, I want to tell you.
Hi. Yeah. Hey, is it okay if I ask a question?
Please do, yes.
Okay, can we go back to the hyperbolic disk slide?
Yeah.
Yeah, could you say what symmetry you were quotienting out by? You kept saying a certain one. Why aren't you saying which one it is?
Oh, well, it's the whatever you would have. Let's take a look at this. So I don't know exactly what it is, so I'd have to tell you. So let's take a look at one of these vertices. Let's say A1, B2. This is one of the terms that I have here, like A1, B2. There is this term, yeah. Can you see where I'm pointing with my mouse?
Yes.
With the pointer, so there's A1, B2. But A1, B2 also shows up here, yes?
Yes.
And so let's look at the faces which are incident to A1, B2. There is A1, B1, B2, that's, which is this red thing. A1, B1, B2 is complementary to A2, A3, B3. So I'm trying to see where that A2, oh no, sorry, I don't need to do that. A1, B1, B2 is this A1, B1, B2, okay? So this face is the same as this face. This vertex is the same as this vertex. This face is the same as this face. So what about this one? This one here, A2, A3, B1, is this unnamed yellow thing that I have over there.
Yeah.
So then you can ask, well, what's this one? And you can look and say, oh, well, the thing that sits on the other side kind of is A1, A2, A3. So opposite from A3, B3, B1. So going from here to the opposite side, this red thing would again be A1, A2, A3. So by doing this, you can keep going and populate the entire hyperbolic disk, and you see that the pattern repeats itself. There is some symmetry that tells you by which you would have to mod out the hyperbolic disk to get a single fundamental domain. So I don't know exactly what it is, but this is how you would find it.
Okay.
Did I answer the question?
Yeah, more or less. I was just thinking that, so this is only one inequality that you're looking at right now? Like perhaps if you...
Yeah, this is a specific one.
Yeah. So maybe if you looked at different ones, like you could, say something about, the symmetries that make up the fundamental domains and try to classify those also, or something like that.
I'm going to focus in this. So this is not so in the rest of the talk, I'm going to focus not on this isolated example, but on the infinite families.
Yeah, okay.
The infinite families live on the torus, the projective plane, and we will have a lot more things to say about them. So that will be my focus. In terms of checking to see if this approach applies to like all inequalities that are there, well, if you had asked me this question like 3 months ago, then I said maybe, I would say maybe, because I only had a limited set of examples and it covered all of them except one. And you never know if that maybe we were missing something. But since then, Sergio Cuenca and Veronica Hubini and Frederick Jia made this list of 373 more inequalities. Many of them cannot be written down or cannot be represented in the form of a graph. And so I cannot tell you how general this story is about the inequalities. I can tell you that for some inequalities, this is clearly the organizing pattern. So I'm going to focus on the geometry of the torus and the projective plane from now on. Okay, so hopefully, again, I am not seeing the audience, so I don't know if I'm not getting any visual cues if my answer was okay, but I'll continue. So I haven't told you one thing, which is very important, which is essential to really talk about these graphs and inequalities, which is what is my role for determining which node and which face are next to each other? Yeah, I mean, you could say, oh, give me an inequality, just draw a graph with however many vertices and faces and pop them here, here, and you're done. Well, that's not how it works. There is a specific rule for which faces are incident to which vertices. And what is that rule? A node, which is a right-hand side term, will be incident to a face, a left-hand side term, if and only if the technical term is do not cross. What does it mean that they do not cross? Either so the other way around. They will not be incident if they cross, because it's an if and only if statement. They will not be incident if they I'm sorry, I said it in a confusing way. So I'll try to start again. And a node and a face will be incident to one another if they do not cross. What does it mean that they do not cross? It means that one is either a subset of the other, or if they are completely disjoint. I'll say it one more time. A node and a face, that's a right-hand side and left-hand side term, will be incident to each other on the graph if and only if either one contains the other or they are completely disjoint. So let's take a look here. I have an A4, A5, B3. I have an A3, A4, A5, B3. This is a subset of that, and therefore this node is incident to this face. So that's a special case of that rule. So all the graphs that you have seen on the previous slides were drawn by applying this rule. We made faces and nodes, and we put them together based on whether they did or did not intersect each other and if they contained one another by this rule. Are there any questions here? Now I can ask a question, which is, what is so special about this rule that they do not cross? Well, what's special is that we, in the language of holographic duality of the ADS-CFT correspondence, we say that terms that do not cross, to them we can apply the entanglement wedge nesting theorem. So entanglement wedge nesting is a statement that if I have some region and another region, and that region is a subset of the larger region, then we cannot have this situation that a subset has an entanglement wedge which reaches deeper than the entanglement wedge of the larger set. So this situation here does not happen. Entanglement wedge nesting tells me that it does not happen. In terms of the graph, I'm making faces and vertices incident to each other if and only if I get to apply entanglement wedge nesting in talking about those minimal cuts. This example here is for a case where X is a subset of Y, but X could be a subset of Y complement, in which case X and Y would be disjoint. So that's why we have these two options. Either one contains the other, or if they are fully disjoint. In both cases, I have a theorem that their entanglement wedges, well, nest. Another way to say it is that their minimal cuts cannot intersect. So this is a situation that cannot happen if I have a nested configuration. So their minimal cuts do not cross. And so this graph represents, in terms of faces and vertices, their incidence relations, basically what I already know about minimal cuts that do not cross. That's another way to say it. Are there any questions about what I just said? I assume that the answer is no, so I'll keep going. But I do encourage questions. So I told you so far about what the faces are and what the vertices are. But when we talk about graphs and graph theory, we really usually say that a graph is a collection of vertices and edges. I just told you about vertices and faces. So what are the edges? And so here is a statement. Edges are little pieces are basically conditional mutual informations. Every edge in this graph represents a single conditional mutual information. Let's take a look at an example. So I'm going to focus on the edge here, which connects A2, A3, B1, and A4, A5, B3. And I remind you that I work in a context where all of these regions together are in a pure state. So I can always flip any one of these terms to their complement. Let's look at the terms that are related to this edge. Well, every edge separates two faces from each other, and every edge has two nodes at the beginning and the end of it. So we have two nodes, that's two positive terms, and two vertices, that is two negative terms in the inequalities. I wrote them out for this edge in this line here. Now, because I'm working in a pure state, for each of these regions, so this doesn't yet look like a conditional mutual information of anything. But because I'm working in a pure state, each one of these terms can be traded for the entanglement entropy of their complements. So I've done it here and going to the next line. And what do I write here? A1, A2, B2, A1, A2, A3, B2 is still A1, A2, B2, A3. But then here, I traded A3, A4, A5, B3 for the complementary region, which is A1, A2, B2, B1. And I've done the same thing for this other term over here. Look at this structure. I have some region attached to A3 plus the same region attached to B1 minus that same region and minus that same region with A3 and B1 put together. This is exactly the structure that we have in a conditional mutual information. This is a conditional mutual information of A3 and B1 conditioned on A1, A2, B2. And so we see that this edge, and this will be true for every edge in this graph, is actually a single conditional mutual information. Now I remind you that conditional mutual informations are non-negative because of strong subadditivity. And so every edge here represents something which is non-negative. And so everything in this graph together can be understood as a sum of certain conditional mutual informations. But there is an additional term over here, which is not part of the graph. This thing does not enter, this single term does not enter any crossing relations with the other terms. It is not, therefore, it is not part of a graph. It cannot be incident to any vertex. And so another way to writing what we have here is that the inequality basically takes the form, a bunch of conditional mutual information. These are the edges of the torus, are greater than or equal to that single term over here. Strong subadditivity tells me that this combination of conditional mutual informations is non-negative. So by strong subadditivity, I just know that this sum of conditional mutual information is greater than or equal to 0. The holographic inequality improves that by putting a non-zero right-hand side. So not only are these conditional mutual informations together greater than or equal to 0, they're actually greater than or equal to some positive quantity. So this is a strengthening of strong subadditivity, and that strengthening follows from the minimal cut prescription. So this is the structure of these inequalities. I focused here on the toric inequality, but there's the projective plane inequalities work kind of similarly. And so in the rest of the talk, I would like to ask, what does it mean in holographic duality, and what makes it true? And I don't know if I'll have time to talk about both of these things, but summary is that at least in certain cases, we can understand this inequality in purely geometric terms. And so that's what I'll tell you first. And for the second question, what makes it true? I'm going to tell you that these inequalities truly hold for an essentially topological reason. And so they're not accidents or they're not like funny quirks, but it's a topology of the problem that makes them work. If you ask me, this is a topology of what? then my tentative answer, although I cannot really be more specific about it, is that it is a certain topological property of holographic error correcting codes. So this is the plan for the remainder of the talk, to talk about these two things. What does it mean geometrically, and what makes it true topologically? Are there any questions? So if there are no questions, then I'll keep going. And so first, for the geometric interpretation of what these inequalities may mean, consider a pure state on many A's and B's, okay? And picture those regions A and B, so AIs and BJs, as living on two circles. This is the A circle and the B circle. So we divide the A into many little regions, and we call them AI. We divide the B circle into many little regions, we call them BJ. This is exactly where this inequality should apply. Now, we would like to ask about, we have to be, for this inequality to not be trivial, I need all the A's to have some kind of entanglement with the B's. Otherwise, this term here would be 0, and then the whole inequality would just collapse to a bunch of strong subadditivities, so it wouldn't be interesting. So the inequality is only interesting if this term is non-zero. Well, if this term is non-zero, this is the entanglement of all the A's and all the B's. And that means that holographically, if I consider this setup, I'm really talking about a two-sided black hole. Here I'm assuming that I'm in a two-dimensional holographic CFT. This dotted thing here is the black hole horizon, and it is this term in the inequality. So we would like to understand what this inequality means geometrically in this setup where the last term here is the black hole horizon for a two-sided black hole. Now, let me redraw, just to make things easier, let me redraw the same picture kind of from above. So here's the A circle drawn on the outside. Here's the B circle drawn on the inside. And then this black hole horizon is some surface which lives in the middle. And looking at this picture, we have to remember that this is actually a minimal surface that separates A and B. This picture doesn't render this, but it's a fact. Okay, so now let's look at some term in this inequality, such as the entropy of AI plus BJ minus. So that would be the entropy of some set of consecutive A's and some set of consecutive B's. I have drawn them on the right-hand side picture like so and like so. And now, generally, the entropy of this combined region, a bunch of A's and a bunch of B's on two different sides of a two-sided asymptotically ADS black hole. Generally, the entanglement entropy of such a region can be in one of several phases. So one phase is kind of like this. I just this is a three-dimensional bulk geometry. So the Ryuta-Kayanagi proposal will just give me geodesics. I'm just going to draw geodesics which directly subtend those boundary intervals. That's one phase. But here's another phase. I can have those geodesics go, both of them, sort of the wrong way around the black hole horizon. So rather than going this way, I have now sent them that way. And this surface also satisfies the conditions for of the homology condition in the Ryuta-Kayanagi proposal. So this is another phase. There are still more phases. For example, we can be in a connected phase like this. And in fact, this is not the only connected phase, because here too, I can choose whether my geodesics will go this way, or maybe they could connect, maybe so they could sort of wrap around the horizon and connect that way. This seems kind of funny, but in general, you have to consider more than one type of wrapping to really get a full phase structure of these Ryuta-Kayanagi surfaces. And so we have a bunch of terms, a bunch of phases, and each of these terms picks one of those phases, and then apparently after all is said and done, and we have picked the phases and substituted the lengths of these geodesics, we must have this inequality be true. And so why is it? Are there any questions about the setup I'm looking at? So I'm applying the inequality to a very specific setup where the boundary CFT is two-dimensional and it consists of two circles. Okay, so suppose, just to make things simple, suppose that this region AI plus and Bj minus can be only in one of two phases, which is either this phase or this phase. So either directly subtending the intervals or subtending the complementary intervals. So in other words, let me assume for simplicity, this is just for simplicity, that, that I don't have to worry about the additional phases which are connected between the boundaries. Well, if that's true, then every conditional mutual information, every edge in the graph looks like a term of this type. Okay, so here I just rewrote for you a formula from a previous slide where we concluded that the edges of the graph are the conditional mutual informations. And you see that this conditional mutual information, think about what would happen if I took a limit where the number of A's and B's goes to infinity. If I made the division of the A circle and the B circle finer and finer and finer. This combination here, which is the conditional mutual information, would become a discretized version of the second derivative of this entanglement entropy with respect to A free, so let's say the right endpoint of the A region, and B1, let's say the left endpoint of the B region. So it's a second derivative with respect to this and this. And now I ask you, do you see that such a second derivative necessarily has to be zero? Why does it have to be zero? Because the entropy is an entropy of a red piece plus a green piece. If I ask for a second derivative with respect to where this endpoint is and where that endpoint is, well, the entropy is a sum of a red term and a green term. There is no joint dependence on this endpoint and that endpoint. This one varies separately and this one varies separately. There is nothing in the entanglement entropy that depends jointly on both of those endpoints. If I take a second derivative with respect to this endpoint and this endpoint, a second partial, I will just get zero. And so it appears that every one of these edges, it was going to be non-negative. It is non-negative, but it turns out to be zero everywhere. Is my inequality even true? It seems that all of these CMIs are just zeros. So am I not just getting zero greater than or equal to this entropy? But there is a special case where it is not zero. And the special case is when the region that I'm looking at, this red and green region, happens to be at the phase transition point between these two phases. If I'm in the phase transition point, then by including the A3 and the B1, I can go from one phase to the other phase. And flipping from one phase to the other phase will give me, if that happens, then I will have a joint dependence on A3 and B1, and I will have a non-zero conditional mutual information. So what we have learned from this analysis, it may have been too fast for you, but and I'm sorry about it, but what we have learned from this analysis is that if I take a continuum limit of this inequality with many A's and B's, then the inequality will entirely localize on the phase transition between one phase and the other phase. So in summary, the inequality after taking a limit of many A's and B's will roughly have the form, the integral over the locus of phase transition between those regions, and after you go through the derivation, cross all the T's and dot all the I's, you get an expression which looks like this. So the inequality becomes that in the limit of many of a fine graining of the A and the B circle. Now, have we seen this formula before? The answer is yes, and I should credit here my other graduate student Bowen Chen and Dachen Zhang, as well as Pavel's current postdoc and my former student Bowen Chen, and my postdoc Ricardo Espindola, who are collaborators on this work. On this slide is their work in progress. So we have massaged this inequality by taking a limit of many A's and B's, so fine graining the A and B circle, and we have arrived at this rewriting of the inequality. And I am now asking the question, have we seen the left-hand side of that inequality? And the answer is yes, we have. This thing is what's called the differential entropy for a curve which which is just tangent to all of these Ryuta-Kayanagi surfaces, or just the transition point. Differential entropy is something that computes the length of a curve which wraps around the horizon, but doesn't quite sit on the horizon. So the expression we found for the left-hand side of the inequality in the limit of continuously many A's and B's is in fact the length of some curve which wraps around the horizon like this. The inequality tells me that that curve is longer than the dotted curve, which is the minimal surface separating A's and B's. And so this is the geometric statement that the inequality has revealed for me. When you look at this, all right, so that's what I wanted to show you. This is the geometric interpretation of the inequality in that phase. Now I made a simplifying assumption that other phases can just be ignored. So the more complicated version of this argument would take, and this is what the Dachan, Bowen, and Ricardo's ongoing work is on, a complete version of this argument would take into account all the different phases that you can have, and their more complicated structures may show up, or at least the analysis is more complicated. But here I focused on one example, and we have seen that in that example, the inequalities basically reveal a geometric fact about certain curves being longer than some certain other curves. So that's a geometric interpretation for what these inequalities mean. I think you will agree with me that if you just stare at the inequality itself, it would be very difficult to guess that it would have an interpretation of this type. And one more thing is that this curve is actually drawn by looking at where the phase transition in the entanglement entropies are. So this is a differential entropy for a curve, which is just tangent to those RT surfaces which are right at the phase transition. And so this curve itself encodes where the phase transitions are. So it's some non-trivial information about the phase structure of the entanglement entropies. Are there any questions or comments? So if not, I'm going to go to the second question I wanted to ask, which is, okay, so you have seen what these inequalities might mean geometrically. The next question is, what makes them true? And the answer that I want to convey to you is that it's a topological thing. So I will be super brief here because there's no way to really convey that in detail. But here is a sketch of how you prove these inequalities. You prove them by constructing tables like this, where every term on the left-hand side is gives me one column of a table, and every term on the right-hand side gives me another column of that table. And then I vary all possible choices of zeros and ones in the left-hand side columns. So here I have 3 terms, and therefore I have 8 different regions. And then I have to find a combination of zeros and ones for the other columns, which satisfies a certain property. What is that property? If I think of the left-hand side terms as x and the right-hand side terms as f of x, then the map from x's to f of x's should be a contraction. This is the condition for a contraction. And there's one extra condition which I haven't told you about, but basically this is the way in which you prove these inequalities. So just to demystify a little bit what this proof technique might mean, here is the kind of contraction table for a simpler inequality, which is strong subadditivity. And you see there's a 0, 0, 0, 1, 1, 0, and 1, 1. Those 0, 0s on the left-hand side, or the terms on the left-hand side, correspond to a division of the bulk into regions which are outside and outside the entanglement wedge of AB and BC, or inside and outside, that's 1, 0, inside AB and outside BC, or 1, 1 would be inside and inside, okay? So each of these terms here corresponds to one piece of the bulk, or one piece of the division of the bulk with respect to entanglement wedges for these left-hand side terms. And now, what is the meaning of the zeros and ones on the right-hand side? Well, they give us candidate RT surfaces for the right-hand side. So for example, this 1 tells me that I might as well start with a candidate RT surface, which is just this and this. This 1 tells me that you might as well attempt to use this 1, 1 region, as the entanglement wedge for B. This set of free ones tells me that I might as well use the combination of the 0, 1, 1, 0, and 1, 1 regions as a candidate entanglement wedge for ABC together. So the right-hand side, the right-hand side columns in this contraction table tell me a way of setting up candidate entanglement wedges and candidate RT surfaces, which will automatically satisfy the inequality. And if some candidate RT surfaces for the right-hand side satisfy the inequalities, then the real ones do too, because the real ones are subject to further minimization. So the inequality can only be even more true after you go to the actual physical RT surfaces. So this is the logic of these tables. Now, why am I telling you about the tables? I'm telling you about them because to prove these inequalities, so these are the inequalities that my collaborators and I have found. I'm just repeating for you the slide from before, the toric inequalities and the projective plane inequalities. We proved them. How did we prove them? We constructed these contraction tables. How do you construct them? You can imagine that finding a contraction table for this beast, or especially for this beast, which is complicated, well, it's probably not so simple. And so indeed, in the beginning, we generated them by a computer, courtesy of Michael Walter, who wrote some software for finding these things by brute force. And we spent a lot of time in Microsoft Excel trying to understand what these zeros and ones are really doing and why they're there in simplest cases. And so I joke that at that time, we were probably the only theoretical physicists in the world who were using Microsoft Excel for their work, but we did. So we did it, and then we found a pattern. The thing that I want to convey to you is that this pattern is entirely topological. And so I'm now going to tell you how to fill in a contraction table for one of these inequalities. And you don't have to get any details out of it. You're supposed to only get, my hope is that you will only get one statement out of it, which is that all that's running this thing is a topology, is the topology of the problem. So the rules are, or the problem is, in proving these inequalities, is that you have some combination of zeros and ones attached to the left-hand side terms. What are the left-hand side terms? Faces. And so I draw zeros, I put some zeros and ones, an arbitrary combination on the faces of my torus. So this is a torus. And then I'm supposed to assign zeros and ones to the vertices, which are the right-hand side terms of the same graph. And so the question is, how would I decide zeros and ones over here? Here's how I do it. Every time I have a zero, I draw these types of lines, and every time I have a one, I draw these types of lines. That produces a graph of this type for me. And now I ask, this graph necessarily consists of closed loops, because there's no way that this graph can have any, that lines of this graph can split in any way. So they always just make up loops. Within every loop, which is topologic, which doesn't wrap a non-trivial cycle of the torus, which is topologically trivial on this torus, I find a vertex, which is, let's say, bottommost and rightmost, and I put a 1 there, and otherwise I put a 0. And so these are the nodes where I put 1s. If I have a loop that closes at basically topologically a disk, then I put a 1 on the bottommost, rightmost vertex enclosed by that loop. Here is a larger loop. It encloses, this loop closes in here. This loop closes in here. And I look for the bottommost, rightmost vertex enclosed there, that's this one. So that's the rule by which I apply the zeros and ones. You will agree with me that this proof is entirely topological in character. There's a version of this that applies also to the projective plane inequalities, which is maybe a little more complicated, but also based on the topology. And so really, the inequalities work for an essentially topological reason, and that's what I wanted to convince you of. You might ask me, what is this a topology of? Well, remember, the connectivity in the graph is related to these nesting relations. Which region contains which other region? We can talk about what the loops here mean, and I have a lot to say about it, but I'm out of time already. There is some very interesting topology associated with the error-correcting properties of the code that we are describing, and that's what these inequalities are really capturing. This is really the thing that I want to convey to you. Okay, so here are some, I'm gonna skip these slides here and just go directly to a summary. So in my title, I promised, here's a quick look to the title. I promised to talk about entropy inequalities, entanglement nesting, topology of error correction, black holes, Cubohemioctahedron, and maybe the Toric code. So I want to say that I have literally talked about all of these things. I haven't really talked about the Toric code, but trust me, when you go through the details of the proof of the Toric inequalities, you are struck by a similarity to many manipulations and concepts which are relevant to the Toric code. And so my collaborators and I are thinking about the relation between the inequalities and the error correcting properties of the Toric code itself. So that's it, and thank you.
Bartek?
Yeah.
Hi, it's Matt. I have a question. So at the beginning of your talk, you emphasized the importance of inequality being saturated. That indicates a certain region of the bulk that is robust against erasure. So have you thought about when your new inequalities are saturated, the conditions or the configurations that lead to saturation?
I'm thinking about it, and all I can say is work in progress. So I have so just to clarify the status of the statement, we looked at the, on that slide, what I told you is that in the case of subadditivity, you can see it with your naked eye, that's what this is talking about. Whenever I'm getting to a saturation, I am going to a situation where multiple, or oftentimes I'm going to a situation where multiple RT surfaces are coinciding. So I'm just at the phase transition where I will correct against this or correct against that. And, or have the correcting, I will be able to error correct against this erasure or that erasure. So I believe that the underlying mechanism for why these inequalities are even there is about what kinds of erasures we can correct. But to be able to tell you specifically for these inequalities what we are learning about the error correction, I cannot tell you. This is work in progress, and we're trying hard.
I mean, the example that you went through in detail with the differential entropy and the horizon, it seemed based on the picture that one can't be saturated. But maybe there's just a different phase where it is.
Oh, no, that's just, it cannot be saturated, but it cannot be saturated because we chose those A's and B's to have a certain topology on the boundary of the two-sided black hole. But then you change the topology of that, and it can be saturated.
Right. So in that phase, it can't be saturated.
I would say if I put the A's and B's in such a way that the A's make a separate circle and the B's take a separate circle, then the topology of assigning the regions A and B to consecutive regions on the circle prohibits the saturability of that.
Right.
But that was a special case. So the point is that special case will just not lead to a saturation.
I mean, that may already have some information about erasure properties or something, that fact already, potentially.
Right, yeah.
Thanks. One more question coming.
Hi. I have a comment about the Cubohemioctahedron in the same vein as the previous one. So the diagram that you draw, this Cubohemioctahedron is probably a what is called a quotient of the hyperbolic plane by a low index normal subgroup of SL2Z. My question is, do you know of other inequalities that look like these polytopes?
So the thing is that we don't know many inequalities at all. You might say that we just learned 373 of them, so that's kind of a lot, but they're very new, and we're looking at them. Generally, I would say that to the extent to which we have analyzed them, many of them do not look like they are related to graphs in any way. But some of them are precisely the graphs that we already know, with very minor modifications. And so I would I don't have any examples where there is an inequality that corresponds to a Riemann surface with genus greater than 2. I do not know of any such example at present. But it might be that one of the 373 recently discovered inequalities are actually that. We just haven't analyzed them fully yet.
Okay, but there is no known organizing principle about what surfaces appear or what won't appear. Then
No, so the part of the point of this talk is to tell everyone that this is an exciting thing to work on, and I would be happy for more people to work on holographic entropy inequalities. So I'm advertising for many interesting things, and maybe some low-hanging fruit there. If you, yeah, I don't have any specific thing to say here, but there may be things that you can discover there.
thanks.